Hello, everyone. This is Yuwei Wan, comes from Cardiff University. Thanks for you attending the presentation of my work, which is exploiting knowledge graph for multifaceted conceptual modeling using GCN. Here's my information. In general, the presentation consists of four main parts. I will firstly give an introduction regarding the background, research motivations, and research contributions, followed by an overall methodology, and for the third part, case study, I will introduce where the data comes from, how the data is pre-processed, and then how the knowledge graph is built from ontology and how the knowledge graph embedding is applied for multifaceted modeling. For fourth part, I would like to talk about the conclusions and future work. Enormous volumes of information or data are created, collected, and stored, which start as a result of the continuous development of complex systems and sensor devices. This type of data are diverse, heterogeneous, and fragmented. In most cases, the relevant information of different modalities or sources is related to one intricate phenomenon or system in real complex industrial applications. In this context, integrating data from multiple sources is of great significance to obtain more comprehensive and informative information than that of each single data source. The fusion information has been widely used to model a multifaceted conceptual system of phenomena which provides a united and versatile view of understanding of the system and or the phenomena. Figure 1 shows an example of the relevant information from different sources such as inspection data, material data, equipment data, process data, and environment data. Hence, data fusion is one of the hot research topics currently. However, the conventional data fusion approaches concatenate feature vectors to fuse different facets, not considering varying distance metrics across facet boundaries. For example, commonly, the tabular data are directly integrated, which fail to capture the interrelationships and is usually computationally expensive. In this case, one fundamental challenge in fusing disparate facets lies in bridging the semantic gaps among them. Meanwhile, graph structure data is a natural target to cover the domain information in many applications such as social networks. As a typical type of the graph structure data, knowledge graph encodes knowledge in a specific domain that comprise rich relational information among elements. Knowledge graph capture each source domain's intrinsic ontology and achieves cross-links among facets. For this work, given the situation and also the advance of the graph structured representation, we are considering using user network structure and complex relationships to facilitate the utilization of the multi-sourced data. When it comes to the inputs of the conventional machine learning models, they usually take feature vectors representing objects in terms of tabular attributes. In this context, conventional machine learning approaches cannot be directly applied in graph structure data. So, graph embedding algorithms have been proposed to learn the representation of the graph structure data. However, graph embedding algorithms suffer from two major limitations. Firstly, the implementation of embedding methods are accompanied by a high computational cost because that there are no shared parameters between nodes in the encoder. It also means the number of parameters increases dramatically with the number of the nodes. Secondly, it is difficult to apply the same graph embedding models in different graphs, especially the embedding methods are unable to handle the dynamic graphs. In To address these two limitations, graph embedding based on GCN have been designed to learn the both structure information and node features for the graph embedding in an end-to-end manner. Firstly, compared with the conventional graph embedding methods that learn the features of the node in a specific order, GCN propagates each node uh, respectively, which leads to the ignores the input order of the nodes. In this context, GCN avoid transversion or possible orders for presenting a graph completely, which leads to the high computational cost. Secondly, each node of graph is propagated with the shared parameters between nodes, which also avoid high computational costs. Thirdly, unlike conventional graph embedding methods, that the state of the edge is represented as the state of the connected nodes. GCN learns the hidden information to update the information of nodes by a weighted sum of the information of their neighborhoods. Given all the situation and backgrounds, I have summarized the contributions in 4 different perspectives. Firstly, we have proposed that the KG provides a promising way to fuse multiple data for bridging the semantic gaps of the disparate data sources. Secondly, we have prepared a graph embedding model based on GCN to convert the notch graphs into a low-dimensional space. Thirdly, we have provided a comprehensive evaluation with a detailed analysis of the experimental results and comparison with different prevailing machine learning models. Lastly, we found that the feasibility of the proposed model was validated in a real-world case application. In this part, I will introduce the methodology. Figure 2 shows the flowchart of the construction of the knowledge graph. In this study, a knowledge graph construction approach using ontology and data is used, which includes 2 stages. For stage 1, the relations among data blocks from multiple sources are identified that they all contribute to one phenomenon. According to different applications scenarios, various types of the multiple sources exist in industrial applications such as different sensors, different modalities, different features. Subsequently, the data that contribute to one phenomenon need to be collected and prepared for the multifaceted conceptual modeling. In stage 2, a knowledge graph construction approach using ontology and data is used. Firstly, an ontology is built in a specific domain, including a set of relevant concepts and their relations. Then the data collecting from multiple sources is fed into ontology to generate knowledge graphs. As shown in Figure 2, the knowledge graph contains information of the entities and the relations is represented by V and E after importing multi-source data. Figure 3 shows a flowchart of the random forest GCN model based on graph embedding. Specifically, the knowledge graph embedding process includes 3 stages. Firstly, the node feature matrix and adjacency matrix are obtained and computed from knowledge graphs respectively. In other words, the entity's attributes is represented as the node features, and the relation features is represented as adjacency matrix are used to express the knowledge graphs. Secondly, a 2-layer GCN model is built to take the 2 matrices as inputs to the for the representation learning of the knowledge graphs. For each node, the feature updates itself by its neighbors with the shared parameters. Thirdly, based on the knowledge embedding, the information content by nudge graphs is converted into embedding features, which are appropriate mm, to be inputted into machine learning models. As the outcomes of the GCN model, the embedding features are accomplished at the level which can be regarded as a feature extraction from the nudge graphs. Then I will introduce data description and preparation. We collected data from an electric steel manufacturer where a reversing mill is equipped for the cold rolling process. Based on our previous study, the relevant data that contribute to the breakage are collected from such as hot rolled, coiled, emotion recorder, and cold rolling process, and so on. Based on our previous study, the data from 5 sources are collected. Figure 4 shows the flowchart of this process of the steel industry. For the former 4 sources, the relevant features that contribute to breakage phenomena were collected. In the last stage, the labels of samples were recorded and collected. Table 1 shows the details of the relevant features for the former 4 processes. The dataset is collected and stored, which covers the production period of the 6 months. For this historical dataset, 956 of them were labeled as noble, while 368 of them were labeled as breakage. In this case, the dataset is regarded as an imbalanced dataset. For the typical machine learning models, 4 different models were selected to classify the breakage samples from all samples. For the performance metrics, the accuracy is typically used as a performance metric for binary classification tasks, but it is not sufficient for the imbalance problem. So the array and the receive operating code was also implemented along with the accuracy to evaluate the performance of our models. Then I will introduce the results and discussions. Figure 5 shows the accuracy across different machine learning algorithms. The comparison reveals that the random forest model shows advantages over the other 3 machine learning models. The MLP model and the SVM model achieve much better performance on accuracy than the CMB model. And Figure 6 shows the AUC across different machine learning algorithms. From the figure, we have some following observations. The comparison reveals that the F model also shows advantages over the other 3 machine learning models. The experimental results show that a significant reduction in terms of AUC was found in the using the CMB, MLP, and SVM models, while the F model performs best on this metric. Specifically, the F model achieves the best AUC comparing with other models. In this context, the F model presents the potential for the imbalanced datasets. Typically, conventional SVM MLP algorithms perform barely satisfactory for the imbalanced dataset, which was revealed in the experiments that these 2 models obtained low value in terms of AUC. For the last part, I summarized the 4 conclusions. Firstly, as a promising way, nudge graph was proposed to fuse multiple data for bridging the semantic gaps among disparate data sources. Secondly, a graph embedding model based on GCN was prepared to convert the nudge graphs into a low-dimensional space. Thirdly, a comprehensive evaluation with a detailed analysis of the experimental results and the comparison with different prevailing machine learning models were provided. And lastly, the feasibility of the proposed model was validated in a real-world case application. And for the future work, a more effective way of constructing the nudge graph will be explored. And meanwhile, based on the characteristics of the notch graphs, optimization strategies is necessary to improve the proposed model in the future. And lastly, a more representative and informative way of extracting the representation of notch graphs will be exploited. This is my presentation. Thank you for your listening.